Welcome to our discussion on putting numbers in perspective, or more precisely, scientific notation. So basically, everything here is going to be talking about large scale numbers and small scale numbers and how we can represent those with scientific notation. So what is scientific notation? Well, it's kind of a shorthand that scientists tend to use a lot, thus the name. And it's basically a way of taking numbers with a lot of zeros and shrinking them down. Either a lot of zeros after the significant digits or a lot of zeros before the significant digits. So a lot of zeros after a decimal or just a lot of zeros at the end of a number. You can shrink those down and just talk about a number and a power of 10. So the idea is, and it's very simple, scientific notation is always one number, a decimal, and one more number, right? So it's always two significant digits. All right, one digit, a decimal, and one more digit, and then a power of 10. So that's the rule. So any number, whether large or small, can be shrunk down and written in scientific notation, because 10 to the 9 just means 9 zeros. You're basically multiplying this by 10 9 times, and you can see that if we started with a decimal here, right, 6.7, and then multiplied it by 10 9 times, 1, 2, 3, 4, 5, 6, 7, 8, 9, we would get back to whatever that is, 6, I think that's 6,700,000,000. And then the same here, if the decimal place has to go in the other direction, right? So 2.0, so if we put a decimal here, right, because this would be 2.0 here, then it would have to go backwards. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So because it went backwards, it's a negative 15 because you're basically dividing, right? You take the number 2.0, divide by 10 15 times, and you get 0.0000, right? All those zeros with a 2. That's all scientific notation is. It's a shorthand for listing very big numbers and very, very small numbers. It also means that you oftentimes have to round to get something in scientific notation. Okay, an order of magnitude is just telling you how large a number. It's something on the order of blank, and it's always a power of 10. So something in the 10,000s or in the millions or in the 10,000ths, right, with a th meaning really, really small, that kind of thing. We can look at order of magnitude of big numbers and small numbers, and then we can deal with those with scientific notation. So if we wanted to try and figure out a reasonable guess for the annual ice cream spending in the United States, we would take a reasonable guess for the population, multiply that by how many servings of ice cream each person has, and then multiply that by what we think an average serving of ice cream costs. Well, there are roughly 300 million people in the US, but rather than writing that with a bunch of zeros, we would start with 3.0, right, times 10 to the 8. That's how many people we have. Then we would take that number, multiply it by how many servings we think they get. Well, a reasonable guess is 50 servings of ice cream per year, basically one a week. That seems pretty reasonable. We could be way off, but it makes the math easy. And then if we take that and multiply it by the cost per serving, another reasonable guess is just that it's $1 per serving, which also makes the math really super easy. So the nice thing about scientific notation is I can now just take 50 times 3 times 1, and I get 150 times 10 to the 8. But this isn't in scientific notation, right? I need it to be 1.5. Well, if I go from 150, right, with a decimal here, and I go down to 1.5, that's shrinking it by 100, right? So to balance it out, I got to raise this by 2 more. So that's where they get 1.5 times 10 to the 10th, or roughly $15 billion per year. Here's some other large numbers put into perspective using scientific notation. Here's another example where we talk about the world population and energy consumption. If we look at the ratio of the world population that the US makes up, 300 million out of 7 billion, again with scientific notation, it makes the math a lot easier because instead of having a bunch of zeros that we have to cancel out, we can just do this division. Since this is multiplication, we can have 3 divided by 7. We can also have 10 to the 8th divided by 10 to the 9th. And we know the rule is, right, if we have x to the power of a over x to the power of b, right? So the bases are the same, the tens are the same. We know the rule is just x to the a minus b. So in this case, it's 10 to the 8 minus 9 or 10 to the minus 1. So 3/7 times 10 to the minus 1. If you do 3/7, you get a decimal, and then 10 to the minus 1 just means dividing by 10. The whole thing comes out to 0.043 or roughly 4%. So 4%. So we make up about 4% of the world's population, but we make up about 19% of the world's energy, which means we're using a lot more energy than the rest of the world. But of course, that's counting, parts of the world that aren't industrialized. There are a lot of parts of the world that don't have electricity and things like that. So obviously, they're going to use less energy. All right, some other perspectives of numbers is the idea of scaling. You've probably all seen a map. You've all seen a scale in the bottom of a map, and it's basically just telling you that this distance on the map equals 1 kilometer in the real world. And if you were to crack out a ruler and measure this, this is 1 centimeter. And if 1 centimeter equals 1 kilometer, then that's a scale of 1 to 100,000 because there are 100,000 centimeters in a kilometer. Now, if you don't have that memorized, well, are you crazy? Everybody should have that. No, I'm just kidding. There's a really easy way to do these types of conversions, and it's called the conversion line, right? So if I start with 1 kilometer and I want to know how many centimeters that is, all I have to do is start canceling out what I start with and get to where I need to be. So if I want to get rid of kilometers, I need a kilometer down here. And then each of these little sections has to be a fraction equal to 1. So if you don't know how many centimeters are in a kilometer, maybe you know how many meters are in a kilometer, right? There are 1,000. That's 1,000. That's really poorly written. Let me try that again. There are 1,000, oh, much better, meters in a kilometer. And now, right, the kilometers would cancel. And now my 1 kilometer is now 1,000 meters, but I don't want meters, I want centimeters. So I know 1 meter is 100 centimeters. Now the meters cancel. And now if I multiply these two together, that's where I get 100,000 centimeters. See, so 1 kilometer got me 100,000 centimeters. And that's the conversion line. And you can use it to convert anything. Another great example of the conversion line is, let's say you want to take something that, let's say you have something that does 100 feet per second, right? You have some projectile that goes at 100 feet per second, and you want to know what that distance or what that speed is in miles per hour, because most humans don't understand feet per second as a measurement of speed. If you tell them 100 feet per second, is that fast? They're like, I don't know, maybe. Is it really fast? Is it faster than a car? So let's convert it to miles per hour. So we get our conversion line out. And let's convert feet. So we want feet down here and miles up here, and we know that 1 mile is 5,280 feet. And so now, if we did the math, this number, whatever 100 divided by 5,280 is, would be miles per second. But we don't want miles per second, we want miles per hour. So 60 seconds in 1 minute, and that's going to cancel out, right, the seconds. And then finally, 60 minutes in 1 hour. And now the minutes are going to cancel, and you can see that all that's left is miles on top and hours. So when we do the math, our answer is going to be in miles per hour. And if you do the math, 100 times 60 times 60 divided by 5,280, you get an answer of, if we just round to a whole number, basically 68 miles per hour. So now you know that projectile that was going 100 feet per second is basically going 68 miles per hour, and you know it's going about the same speed as, a car on the highway. And it gives you a better perspective of how fast that thing is going, all based on converting things using the conversion line. All right, here's another example of the distances of the Earth and the Sun and how big the solar system is. I don't want to waste a lot of time on this. You can read through these if you want to. It just gives you an idea of scaling them down if you want to make like a scale model of the solar system, right? So pause the video and read through this if you want to know. Another idea is figuring out how big a billion really is by figuring out how many people it can employ. Again, I'm not going to spend a lot of time. Pause the video and read through these if you want to. It all comes back down to the conversion line, right? We can set up $1 billion divided by in people. Now we have money per employee. Go on there, and then it tells us how long would it take to earn $1 billion. Right, so all of these examples come back to the idea of the conversion line. It doesn't matter what you're converting, just each section of the conversion line is always a fraction equal to 1, so top and bottom have to be equal to 1, like 12 inches in a foot, 3 feet in a yard. If we're in the metric system, it's really nice because they're all just powers of 10, right? 100 centimeters in a meter, 1,000 grams in a kilogram, things like that. And then you can change magnitude and put numbers into perspective.